These are the notes for LT3 in the Space Science unit. And target says I can calculate force, mass, or distance using the law of universal gravitation. I've actually simplified this down. We are only going to calculate the force of gravity, so just the force part. You need to understand the relationship between mass and distance in this force, but in terms of number crunching, we are just going to calculate the force. As we do this, absolutely you have to have a calculator. You need to have a formula sheet. All right, so the formula sheet, whatever color it is, depending on the try you have me, as well as LT3 practice problems. I think there is a copy on Moodle if you needed to look at it there. In terms of the notes, there's not very much to write down. When you see the word universal, just think of it as applies to absolutely everything and everywhere, okay? So this isn't just happens on Earth or just happens between planets. This happens, this is a relationship for absolutely every object, every proton, every photon, anywhere within the known universe, all right, even what we don't know. So in terms of concept, it's the only thing we write in the notebook is what does this thing mean? All right, so this is our formula for the universal law of gravitation. So F-grav is equal to capital G, which is the constant, m1 multiplied by m2 over d squared. m1 and m2, these are just objects. Typically, one of those is going to be a planet or a moon or something really big, but it could be something as simple as your dog and your cat. All right, so just anything that has mass could technically be within the numerator there. The d is the separation distance between those two objects. So hopefully you've already mastered LT2, which talks about this inverse square law. So this being in the denominator should look familiar. So we know as things get farther apart, the force between them goes down very quickly, all right, because of the fact that that gets squared. All right, so the separation distance. The capital G is a constant, so once calculus was discovered, Newton was able to calculate what this number was. It never changes. It is 6.67 times 10 to the negative 11th. Okay, this should feel really familiar because you did a similar equation back in electricity. Q1 and Q2 were two different charged objects, and then the constant was a different number. But in terms of steps and solving, this should be very familiar to you. What this means, if we were to write this not in scientific notation, we would have a decimal, 10 zeros, and then 667. All right, so think about that. 10 zeros into 667. So if I say, is this a big number? I don't mean like, is it a long number to write out? Of course it is. That's a lot of digits. But like, that's not even close to 1 even. So when you look at two normal-sized objects, you look around the room and say, okay, a table and a chair. Because we multiply them by this, that's why those things are not gravitationally like thrown into each other. Because of the fact that gravity is actually a super weak force. Whereas with electricity, remember K ends up being like 9 billion. That's why electricity knocks you on your butt. But gravity, because this thing is so small, unless you have something ginormous, like planet, moon, stars, you don't even really feel gravity. Okay, something has to be really big. And that is all there is for the notes. Okay, so the notes are just understanding what's going on there. This is where you need to be able to calculate some things. So I've already given these in class. I'm going to give you a second to write these steps down on your formula sheet. All right, so the first step is you multiply M1 and M2. You hit enter. The second step is you divide by d squared. I have a little arrow pointing to the 2. That's because people forget that squared. All right, so after you multiply your objects together, their masses, you divide it by the distance squared. And then your third step is to multiply it by the capital G, that constant, which is 6.67 times 10 to the negative 11th. So pause me if you need to, because I'm going to keep right on rolling here. Practice problems. I'm just going to pick a couple of them to work through with you. It's the exact same process every single time. we're going to do 2 and 5. All right. So have your formula sheet kind of off to the side, and step by step, we're going to go 50 multiplied by 300,000. We hit enter. There's the intermediate step 1. There's no need to write down the in-between answers. It doesn't matter. We divide it by not just the distance, but the distance squared. So 675 caret 2. Remember, the caret means squared. 2. Hit enter again. And then the last step is we divide. I'm sorry, I misspoke. We already divided by the distance squared. Now we multiply by the constant. So we multiply these two, divided by this squared. Last step, multiply by the constant. So times 6.67, and the constant is a times 10 caret negative 11. Hit enter. And if it were me, even in Moodle, it might say to round your answer. That's only if you convert it to scientific notation. Most people will not want to. So I would type it in exactly as this is. So that is a decimal, and then 8 zeros, and a 2. All right, so you would type this into Moodle and get a nice little green check for it. Okay, so the 3 steps never change, same thing every time. I'm going to do number 5 with you just so you can see what happens when you have a big mass like the Earth here. All right, so nothing changes. It's going to be 65, which would be like a normal sized person. Just an average sized person, I should say. Multiply it by 6 times 10 caret 24. Hit enter. So there's an in-between step. 3.9 times 10 to the 26th. We divide it by the distance squared, so 3,000 caret 2. And we get that. And then the last step is to multiply it by that gravitation constant. So multiplied by 6.67 times 10 caret negative 11. Final answer is a really big number this time. So 2890, 1, 2, 3, 4, 5, 6. 6 threes. Okay, but this should make a little bit of sense, because now we've got something as massive as the Earth pulling on a person. So you're going to feel that force. That's why we're stuck here. All right, that's not why we're not just floating around. But you have to have a large force for that to happen. One thing I want to remind you of. Okay, remember Moodle is not super scientific notation friendly. Let's just pretend. All right, this is a pretend world. You got an answer that was 2.767 times 10 to the negative 16th on your calculator. Okay, let's just pretend that's an answer you got. It'll say round to the 10th. So you look here, and that's going to become 2.8. Remember, the letter E replaces times 10. It doesn't matter if it's uppercase or lowercase, but you have to put in a letter E and then negative 16. So this whole thing would be typed in that format. All right, and we did that back in Coulomb's law on electricity, but it's been a little bit of time. So if you needed to write this down on your formula sheet, the E is equal to the times 10 caret, feel free. Now, gizmo, all right, I don't know if you're watching these notes, if you also missed the day we talked about the gizmo, but there are a lot of screenshots. There's probably 8 to 10 questions where you have to know how to work through and how to calculate the force factor, how to calculate MA times MB, all right, how to calculate 1 divided by the distance squared. So you are not ready for LT3 unless you have also completed the gizmo. So whether or not you need to get that from me in class or whatever the situation might be sure you have done this, these, the notes, all of those before you take LT3. All right, good luck.